All right, hey guys. So today is day one of the ROS through simulation tutorial workshop. Um, I'm really excited to help teach it. I'm gonna share my screen here. So this tutorial, it's not yet, but after we get done with it, um, each day I'll be updating our GitHub page. So if we go to the GitHub, in our wiki, we have this page 4, which is learning ROS through simulation with TurtleBot3 and Gazebo. And so I started writing up some blurbs that you can read. But yeah, basically, wait, so we don't actually need a robot to write and test software? No, we don't. That is the very cool feature of simulation. Every bit of software that we write this year, assuming we have a realistically modeled CAD model that we exported to the ROS format that we need, which is called a URDF file, which models the joints and whatnot. So long as we have that, we should be able to simulate physics on them, on each joint and each part that we're writing software for. And so we should be able to fully simulate our rover if we have a beefy enough computer, that is. So with that being said, this tutorial, this workshop series is based around what is called the TurtleBot. So the TurtleBot is actually a family of robots that some company developed. It's escaping me right now, but we will be using this TurtleBot3 family. So the TurtleBot, all the CAD models and everything are all open sourced, and they are all pre-installed once you install the TurtleBot libraries. So we'll have access to all the models and all the control software to control any TurtleBot3 robot. So there's the burger, which is what we'll probably mostly be using. And then there's also waffle and waffle pie. Each of the robots are configured, I believe, with a LiDAR unit and a camera. So we will be able to, in these workshops, make maps and whatnot with the LiDAR unit. And then we'll also be able to use the camera to look around in these simulated worlds. So part one, that's what we'll be doing today. We'll go through installation and setup, and then launching our first Gazebo world. Gazebo is the simulator environment that ships with ROS. And that's how we'll simulate the robot. And then we'll drive around. We'll drive the TurtleBot around the house world, which is one of the pre-compiled worlds. And then we'll also look into creating a map using SLAM. And finally, driving the robot autonomously by giving it waypoints using the map. So super cool stuff. Hopefully you enjoy. Let me know if you have any questions or if I need to slow down. So this is what everyone should be familiar with at this point. This is just a bare bones installation of ROS. Or at least it should be. Let me go into terminal and just verify. This is what I believe this is what we ended on Friday's meeting. I'll actually make it a little bigger just so everyone can see. If we list our Catkin workspace and source, you can see we have the URC code that we installed yesterday. I wanted to preface, I guess, this tutorial by saying simulation is very CPU and GPU intensive. So especially if you're running it off of a VM. And then once it's powered off, we'll be able to access these settings. And in display, make sure 3D acceleration is checked. If it's not checked, at least for me, I was only getting about 1 to 2 FPS on Gazebo, so super slow. With it being checked, I was able to get about 20 FPS, which is much better. So that's the only thing I suggest changing from what we had already looked at in VirtualBox. Another suggestion is if you're on, say, Windows, I would suggest going into your power settings, and for your battery settings, you can either have best battery life or best performance. I would suggest putting on best for performance because, yeah, simulation is so intensive that we need to use the CPU to the max. And then we can hit start again. This will load up the VM. So next we're going to look into installation. This should be pretty straightforward because there is a whole bunch of libraries that we need, but there's a pretty much one-line command that installs most of them. So we could actually install even more. We could install all of them on one line, but it's typically safer to install these first ones first, and then we'll install the other ones on top. The first command that we'll be using. So it should look something like that. I know Zoom may have reformatted it, so someone let me know if it doesn't work just by copy and pasting it directly. And then this will probably be the longest period of sitting and waiting for all these libraries to download and install. So let me know if you have any questions. Let me know if it's not working. While we do that, let me say that this tutorial, I'll bring it back up. Obviously, this is my own adaptation of this tutorial. The original tutorial can be found here, which I will post this in chat for anyone needing it. So currently all those lines that we just selected to install are actually in this, please follow the PC setup. So if you click that, it's all of these right here in step 3.1.3, because we already installed ROS. So yeah, just in case you, for whatever reason, can't copy and paste off a chat or whatnot. It's right here, learn.turtlebot.com. It's actually a very, very good tutorial in terms of it covers pretty much everything we would ever need. Unfortunately, it's pretty outdated. So what I'm hoping to do with this workshop is update these two tutorials. Because this one was on Ubuntu 14. This one is actually Ubuntu 16. Oh, so yeah, word of caution, if you do copy and paste off the website, make sure you go through and rename each of the kinetics to melodic, because that's the ROS version we're using. So now, as you can see, we have finished downloading everything, but it still needs to unpack and install everything. So that's what we'll be waiting on for now. Yes. So this is the other thing. You may run out of disk space because in this case, I had only allocated, I think 10 gigs. I was trying to see how small of a drive I could get away with. And I don't think 10 gigs is enough, unfortunately. So I will quickly show you guys how to increase your storage space in case you ever need it on a VM. So in VirtualBox, what you'll do is up in File, there's a Virtual Media Manager. That's interesting. Where did it go? There it is. So what you'll need to do, I think by default, it looks like this. You'll go into your, you'll click on whatever virtual disk file that you're using. So in this case, I'm on this Ubuntu 18.04.5 ROS and Workshop. You'll go to Properties, and then you'll just use the slider, or you can just enter in right here how much space you want. This was originally at 10. I entered 20, hit Apply. But as you noticed, I'm still out of storage space. And that's because even though I hit Apply, it currently has 20 gigabytes free to use, but the operating system itself only knows of the original 10. So we actually have to go in and use a program. If you're on Ubuntu, I would suggest GParted. So that is sudo apt install GParted. And I will paste this in chat just in case anyone needs it. Just in case anyone is also running out of space. What GParted is a disk size utility, if you will. It can be used to resize, expand, and compress how much storage space you have on each of your hard drive disks. So once that's done, we can go to GParted. There it is. So like I said, it only knows of the original 10 gigabytes, but as you can see, we now have an additional 10 gigabytes of unallocated space. So all you have to do is click on your partition that you have, that you're almost out of space, hit resize, and then here you can either just slide it around however much you want to give it, or you can enter a new size, or however much free space you want to give it. Since it's a VM, I really don't care. I'm just going to give it the entire max, all 20 gigs, and that looks good. It's now all one drive. And so we'll hit the check mark to apply all operations, hit apply. Completed successfully. Okay, exit out of here. And then just to check, we can do a df.h, disk free, human readable. And we can see that dev SDA1 now has a size of 20 gigs, and we're not out of space. We're only 47% used. So there's actually four more packages, 3 of which we'll be installing using apt. So the first one is the Dynamixel, I believe that's how you pronounce it, SDK package, which the command, it looks like that. Let me make this easier to read. This library is used to control the servo actuators, all the motors on each of the TurtleBots. And then once that completes, we will install the next one, which is the ROS melodic TurtleBot3 messages. So this allows us to communicate between nodes. We'll go over this more in our next meeting, but the whole ROS architecture. But ROS is a graph-based architecture. What that means is each code file that we run will produce typically one node. And so you'll have all these nodes in a graph, in which case they communicate with each other. You can communicate between different files that are being code files that are being run using data transfer through what are called topics, basically data streams. Then final library we'll install is that one, which is the main TurtleBot3 package. The next couple commands are to change directory into your Catkin workspace. And then once you're in there, we are going to clone the TurtleBot3 simulations repository. And then once that gets done, we are going to change directories back into the Catkin workspace and then run a Catkin make. That's interesting. I'm wondering why it's what was that?
I think your Catkin ignore is at the root of the workspace. So I think
is it? Aha. Good catch. That's why. Thank you, Turan. Yes, the Catkin ignore needs to be in your C code, not in the entire thing, or else we're not going to build anything. So sorry about that. Let me move the, this will cut and paste, if you will, if you're coming from Windows. I'm going to move the Catkin workspace source Catkin ignore to Catkin workspace source URC code. So now if we list Catkin workspace source URC code, there it is. And if we list just source, it's no longer in there. Cool. Yes, thank you for that. Let's go into our Catkin workspace and run a Catkin make. Aha, yes. So it is now currently building everything. So now that everything is built correctly, we're actually going to need a couple of tabs here. So I'm just going to give myself space. I think for now, 3 tabs will be fine. We're going to run the following commands. So we're going to have this one in our first window. This will load up Gazebo and put the TurtleBot3, the burger model, in the center of the world. Once Gazebo loads, I'm going to show you guys a almost like a cheat code in order to get more performance out of it. Because as you can see, it's going to be really, really slow. But there's a way to limit the physics engine so it's not hogging all the resources, and so it speeds things up. So we go to Gazebo. See how slow it is. We're at real-time factor of 0.08, which means pretty much 1/10 speed of real life. So that command that I said increases your performance is this command. I'll post it in chat. It's really you'll have to try it and trial by error, if you will. You'll have to play with this 0.01 number by increasing the number. So say 0.02, 0.03, it will get faster and faster. And then by decreasing it, it will get slower and slower. So 0.001 will be even slower. 0.0001 will be slower. But by doing that, as you can see, we already went from 1/10 speed to almost full speed. So kind of the trick is playing with that number, figuring out on your computer how to get around 1.0, real speed. Now, the larger you make that number, so the faster you allow it to go. So like we'll actually do, we were close, maybe 1.3. The larger you make that number, the more unstable the environment's going to be. So you'll see the robot start like shaking and whatnot because it can't compute all the physics for it in time. But that looks good. And we're at almost real speed. We can actually probably increase it more. You can actually go faster than real time too. You can exceed 1.0 and go into 2.0 and 3.0. So the final thing is to control the rover, that is known as Teleop, teleoperation, which is remote control. Like if you had a joystick or something, we'll just be doing this through the keyboard. So it'll be this command. So as you can see from the instructions that it gives you to move around, it's WASDX, S to stop everything. So you can just hold down W and it'll speed it up. And as you can see, we're driving the robot around. We can turn using A and D. And if we put A and D to the maximum, it will even point turn, especially if we slow down the linear velocity when we have angular velocity. Now it's just point turning in place. So yeah, there is, if you wanted to, this is something for you guys to explore on your own. There's several different worlds you can launch. It doesn't just have to be this boring blank world with nothing in it. We go back to the simulation. This is the house I was talking about. So it's, come on. Right here, ROS launched TurtleBot3 Gazebo, TurtleBot3 house.launch. I'll post that in chat as well. So yeah, have fun experimenting, loading each of these, experimenting with the GZ physics to hopefully get it to run at real-time speed. And that is it. Next time, we'll look at the SLAM mapping and SLAM navigation, creating a map and autonomously driving around it. And then we will also probably start looking into accessing the cameras and a couple of other sensors. So yeah, I hope to see you next time. And I'm going to stop the recording now. Thanks for joining us today.